Hello and welcome to the last video of topic 7. In the previous video we derived the residue theorem and looked at a couple of examples of how to use it. In these examples we found the required residues by explicitly performing the relevant Laurent expansion. This approach is often reasonably straightforward if you can spot a familiar Taylor or geometric series to manipulate. Here we're going to look at another way of finding residues given knowledge of the order of a pole. This will be really helpful for using the residue theorem to calculate integrals in the rest of the course. As a quick recap of what we looked at in the previous video, we derived the amazing residue theorem. This relates the value of a contour integral to the residues of the enclosed isolated singularities. To show this, we used our knowledge of integrals of z minus z0 to the n from topic 5, and also the deformation of contours through regions of analyticity. We saw that when looking at contours enclosing multiple singularities, we could use the trick of shrinking the contour through regions of analyticity and then cancelling channel contributions. Importantly, this showed us that we need the residue from the Laurent series about each singularity in order to be able to use the residue theorem. These are the intended learning outcomes for this video. After watching this video, you should be able to find the residue at an isolated singularity. At the end of the previous video, as I mentioned, we did this by using known geometric series to directly construct the Laurent series. Here we're going to look at another approach that uses knowledge of the order of a pole. As always, you'll have lots of chances to test your understanding of the material from this topic in the problem sheet. And I'll point out that the first question asks you to derive a few other useful shortcuts to finding residues. Let's begin. In this video, we're going to look at how to compute residues. In the previous video, we did this by explicitly finding the Laurent series, and here we're going to look at another useful way of finding residues. First of all, recall that we can remove a pole of finite order m at the point z0 by multiplying our function by z minus z0. Writing that out, we can consider constructing some new function, g of z, given by f of z that has a pole at z0 of order m, and multiplying that by z minus z0 to the power of m. And that's clear from looking at the Laurent expansion of the function f of z. Its most negative power will be z minus z0 to the power of minus m, therefore g of z will have no negative powers of z minus z0. Therefore we can say that this is analytic at z0, and that means that the generalized Cauchy integral formula and you'll recall that we encountered that in topic 6. That means that the generalized Cauchy integral formula applies to this function g of z. I'll state here that the generalized Cauchy integral formula applied to our analytic function g states that the nth derivative of our function, evaluated at some point z0 inside a closed contour, that's given by n factorial over 2 pi I times the integral along a contour C enclosing z0 of g of z over z minus z0 to the n plus 1 dz. The meaning of this is that on the left hand side we have the nth derivative at some point inside the contour C, and it is given by the expression on the right hand side, which is an integral of values along the contour C. Okay, now let's consider evaluating
the integral along a closed contour C of our function that has a pole of order m. Well, we can rewrite this in terms of g as the integral of g of z divided by z minus z naught to the m dz. We can then immediately use our generalized Cauchy integral formula to rewrite this as 2 pi I divided by m minus 1 factorial. That's noting that the generalized Cauchy integral formula has a power of n plus 1, whereas in this line we have a power of m. So we now have 2 pi I divided by m minus 1 factorial, then times the n minus 1th derivative of our function g evaluated at z naught. I'm going to write this out as a proper derivative, and this is the n minus 1th derivative of our function g of z evaluated at the point z naught. We can now substitute back in terms of f. So we'll have 2 pi I over m minus 1 factorial, the m minus 1th derivative, and we now have that g of z is given by z minus z naught to the m times our function that has a pole evaluated at z naught. This means that we've managed to express our contour integral of f of z as this expression in the bottom line. We can therefore say, but from the residue theorem, we know that this should also be 2 pi I times the residue of our function at the singular point z naught. We can therefore say that by comparison with the residue theorem, it must be that for an mth order pole, we have that the residue of our function f at that mth order pole is given by, and then this is taking this line here and dividing by 2 pi I. So we have 1 over m minus 1 factorial, and I'm actually going to insert here the limit as z tends to z naught, and I'll explain why in a moment. We have the m minus 1th derivative of z minus z naught to the m times f of z. This is a really important result, so I'll put it in a red box. And this is a way to calculate the residue at an mth order pole. You'll notice that I've inserted the limit as z tends to z naught. And the reason for that is that the expression on the right hand side in this red box may be indeterminate, and that means that you have to apply L'Hopital's rule to find the appropriate limit. You'll get some practice at using this in the problems in the problem sheet. So this is a very useful expression for calculating residues, and crucially you have to know m, the order of the pole. I'll also mention that you'll have a go at proving this result using series expansions of functions in the problem sheet. Let's go through an example. Let's check the example from the previous part, where the function of interest is 5z minus 2 divided by z minus 1, and we want the integral around some contour C that encloses the poles. In the previous video, we found the residues by expanding explicitly in Laurent series. But from the expression in the red box, if we know the order of the poles, then we can use the expression given. The first thing to do is to check the order of these poles. We know that we have singularities at z equals 0 and z equals 1. So let's first look at the singularity at z equals 0. You might be able to spot from the function itself that this is a simple pole. There's a little trick that will justify this. You can write the function 5z minus 2 over z times z minus 1 as 1 over z times 5z minus 2 over z minus 1. Now we're interested in behaviour in the neighbourhood of the singularity at z equals 0. And you'll spot that this term here, this is analytic in the neighbourhood of z equals 0. It is not singular. That means that it has a Taylor expansion. We can write it as the sum from n equals 0 to infinity of some coefficients and then non-negative powers of z minus z0. Substituting this in, we have 1 over z, and then the first couple of terms are p0 plus p1z plus p2z squared, and so on. And this gives p0 over z plus p1 plus p2z, and so on. We can easily spot that this is therefore a simple pole, because the lowest negative power is z to the minus 1 in our expansion. In order to find the order of the pole, we didn't have to go through the full process of finding the entire Laurent series. Okay, so we found that the singularity at z equals 0 is a simple pole. That means that we can apply the expression in the red box at the top of the page, that the residue of our function at z equals 0 is 1 over, and then m equals 1, so m minus 1 factorial is 0 factorial, which by convention is taken as 1. The limit as z tends to 0. If we look at the expression in the red box, when m equals 1, the derivative is irrelevant, and we're now left with the limit as z tends to 0 of z times our function 5z minus 2 over z times z minus 1. The z's cancel, and you can check for yourself that when you substitute in z equals 0, this evaluates to 2. And this agrees with what we found in the previous video from the Laurent series. Let's move on to the second singularity at z equals 1. Again, we can rearrange our expression for the function. We take out the 1 over z minus 1, and we're left with 5z minus 2 divided by z. Again, we spot that this is analytic in the neighbourhood of our expansion point z equals 1. Therefore, it also has a Taylor series. And by the same argument as above, we have that z equals 1 is also a simple pole. Using our expression in the red box, just off the screen, we have that the residue of f at z equals 1. This is simply going to give us our limit z tends to 1 of z minus z0 times our function. And you can check for yourselves, this gives the residue as 3, which also agrees with what we found in the previous video. And we can then use the residue theorem to calculate the integral as before. So that's it for this simple example. You'll get more practice in the problem sheet. I'll end this video with a little comment about what technique to use when. This method of finding residues is particularly simple for low order poles. And that's because you only need to take low order derivatives. And clearly this will get messy for higher order derivatives. I'll note that often when dealing with this limit, L'Hopital's rule is your friend. The condition for using the expression we had earlier in the red box is that you have to know the order of the pole. And sometimes it'll turn out that rather than repeatedly differentiating, direct expansion into the Laurent series is a better strategy. That's the end of this last video of topic 7. As a quick recap of the whole topic, we began by looking at singularities of functions and found ways of characterizing those as poles or essential singularities or branch points. We talked about the relationship between poles and zeros of functions. We then showed it's possible to evaluate an integral in a multiply connected region using integration by residues, where the residue is the a-1 coefficient in the Laurent series of your function about the singularity of interest. The residue theorem is one of the most remarkable results in complex analysis, and we'll spend the rest of the course looking at its consequences. In this last video, we looked at a way of computing residues for low-order poles. You'll get lots of practice of all that's been covered in the accompanying problem sheet, and in the first question you'll derive some other nice shortcuts for computing residues of functions of a particular form. So that's the end of topic 7. Thanks for listening.